Hi, my name is Steiger. I'm a senior manufacturing engineer here at Cal Poly. This is my senior project, the eaZ-Bar clutch linkage system. I would like to thank Kurt Colvin for being my technical advisor for this project. Quick rundown of what we're going to go over. I'm going to give you an introduction, my problem statement, background, the constraints of my project, the methodology I use, the final design, and then an economic analysis before the conclusion. I love classic cars, and I really wanted to do a project that involves the restoration or modification of classic vehicles. And then I also have hands-on experience with 60s era Mustangs. This is what led me to choose this project. The problem statement: the clutch swing arm in many classic vehicles is a cumbersome equalizer bar. It's commonly called a Z-bar. It bolts directly into the block in the outer firewall. This Z-bar is plagued by a ton of issues that cause it to fail very frequently. You can see a schematic of the Z-bar here on the right. You can see that it sits on pins mounted to the block and the outer firewall, and those pins are supported by bushings. Then there's the translation bar from the pedal to the Z-bar itself. Some background: the Z-bar has a lot of design flaws. There's very tight clearances. The mounting bracket on the outer firewall is right under the steering column, and it's also right next to all of the exhaust, so it's actually very hard to work on. With its mounting location, the engine vibrations and road vibrations can get into the system very easily, causing it to loosen, causing all of its fastened parts to loosen. Then there's also the friction on the clutch. The rubber bushings are not very good in this system, so they grab onto the pins and they rotate them out of position, and they can eventually cause them to fall out. There's also the mechanical wear. The translation pushrod from the pedal to the Z-bar has no bearings or bushings, so it's just metal on metal rubbing, so it gradually creates a hole, a bigger hole, and slop in the Z-bar system. There's also the insufficient manufacturer that these Z-bars fail under the pressures of normal stock clutches, not even high performance clutches, and they actually had to be redesigned in 1968 just to be able to handle the car's power. This is actually the most common area for Mustangs to have problems and end up in the shop because of these faulty Z-bars. There are currently two linkage replacements. There's the cable and the hydraulic. The drawbacks of the cable is that it requires an entirely new clutch pedal, and it requires a new throwout bearing and clutch fork assembly. For this to be installed, the transmission has to be completely removed from the car, which can be expensive and time consuming. The problem with hydraulic systems is that it damps the pedal movement, so the pedal can only go a certain speed. So if a driver wants to drop the clutch and hit it, they can't. The pedal is only going to go as fast as it's going to go, so it can really impede on the car's performance. For my design constraints, I wanted the new linkage to successfully disengage and re-engage the clutch, be easily depressed, be easily installed by someone at home with some hands-on skills. It shouldn't require any modifications to other parts in the engine bay besides the clutch linkage system, and it should give the driver feedback through the pedal. It should not require modification to the clutch pedal, and it should be easily modified for different model years or vehicles. Initially, I had designed a straight mechanical linkage that would eliminate the outer mounting bracket of the Z-bar. It would be made from aluminum for weight. It would be closed die forged for strength, and then it would be welded. The pivot bars would be welded to it, and I would then have designed all of the fixturing and CNC machining processes. The goal of this design was to have identical performance to the stock system, and I wanted it to be a low-end market disruption, so it would extend a consumer class and then create a new demand. You can see my first design here. There's the unexploded view on the left and the exploded view on the right. I incorporated bearings and snap rings to reduce the friction as well as the mechanical wear in the places that I discussed earlier. But you can see that it's very similar in overall shape to the current system, but it just is more complex, and it eliminates the outer bracket. After talking to Dr. Colvin after my first quarter of senior project, we decided that I needed to take a more systems engineering approach to this process, so I researched more alternatives in depth, and I decided in the end to explore some semi-automated alternatives as well, such as a rotary servo motor and a linear actuator. The semi-automated systems would both be programmed in ladder logic, and they would include a PLC and a potentiometer at the clutch pedal. The only difference would be the way that they physically depress the clutch fork. When it came down to the decision matrix, I used ease of install, price, lifespan, cost of repair, feasibility, reliability, on down to performance to decide which alternative I should go with. I also weighted each one according to their importance. Performance was very high for me, so I wanted to make sure that that carried some of the most weight. In the end, it came out that PLC with the linear actuator was the best alternative I could choose. This decision caused me to need to change my paradigm of my project. My project was no longer a low-end market disruption. I wasn't extending a consumer class, I'm now creating a new consumer class. And now there's also no pedal feedback. Since there's no straight mechanical linkage to the clutch fork itself, I can't give any pedal feedback through feel. And it's also no longer a simple do-it-yourself project. The actuator must be mounted onto the transmission. There's also the running and connecting of the wires and the mounting of the PLC and potentiometer. With my final design, I chose with linear actuator. I'm going to have a PLC mounted under the dash. It's a Click C008 ND3. There'd be a linear potentiometer at the clutch pedal. And this is a 3-inch MIDI-sense linear slide potentiometer. Then there's also the linear actuator mounted to the transmission with a bracket. I chose a 2-inch stroke Servo City heavy-duty linear servo. And then there's also the actuator programming in ladder logic. I programmed this in RS Logix 5000, but the Click PLC actually comes with its own programming software that is in ladder logic, and it is free with the purchase of the PLC. With my linear potentiometer placement, I wanted to mount it on a post with stops so that the pedal travel could not exceed the maximum travel of the potentiometer and break the system. I also wanted to use the same pedal mount location here as the current system and the same hole through the firewall as with the current system. This is shown as a hydraulic system here on the right, but it does use the same locations as the current eaZ-Bar system. Then there's the linear actuator mounting. The linear actuator would mount onto the transmission here and use the same bolts that the transmission bolts onto the bell housing with. I designed this bracket to mount the linear actuator onto, and the linear actuator would actually sit behind the clutch fork, so it would actually pull instead of push the clutch fork from its location. This is my ladder logic program. I latch state 1 when the key is turned on so that the clutch is working as soon as there's power supplied. In state 1, I divide the pedal potentiometer location, it's between 0 and 5 volts, by the maximum, which is 5 volts, to get a percentage of the pedal location. This percentage is then multiplied by the actuator extension potential, which I have declared to be 1 inch so that I don't overextend the linear actuator. Then this is used to create a motion axis move. The axis is the actuator. I wanted the position to be real, and I wanted the speed to be 90% of the maximum, the acceleration to be 50% of the maximum, as well as the deceleration. And then the acceleration and deceleration jerk are 100% set on default. And the lock position is the position that the linear actuator is being told. For the cost analysis, the biggest cost was the Servo City actuator. You can see that the direct material comes out to $338.35. The Servo City actuator is actually almost $300 of that. Then there's the operator wage of $15 an hour, but my only operator requirements were to plasma cut the bracket, and the bracket only takes 1 minute to be cut, so this only costs 30 cents. So the total cost of the system comes out to be $338.65, not $338.35 as I have there. This product could then be sold for $500 to $600 to make a sizable profit for the manufacturer, because it's more of a systems integration more so than a product that is being made. So it's all about outsourcing. And then for the consumer, repairs to the standard clutch can cost up to $300, if not a little bit more. And from personal experience, I've had my Mustang for 8 years and my linkage has needed to be repaired 3 separate times. So as a consumer, it makes sense in the long run to purchase the automated clutch system as opposed to continually repairing and adjusting the current system. In conclusion, I faced several challenges. The force required at the clutch fork came out to be 103 pounds, and it was hard to find a servo or a linear actuator that could do that at 12 volts. I'm limited by the automotive electrical limitations of a 12 volt battery, and a lot of servos and linear actuators that had the potential to put out 103 pounds of force needed upwards of 100 volts in order to do it. I also found some that were able to use 12 volts, but they were very slow and they would cause the car to have terrible performance because it would take upwards of 3 seconds just to disengage the clutch. Other than that, the cost, it makes business sense for the consumer and the manufacturer to design and purchase this product.